across the country and around the world. The success of the Kepler mission is a tribute to those people's efforts, and I tip my hat to each and every one of them. I'll turn it over to Bill now.
Thank you, Doug. What I'd like to present today is the results of the first 4 months of science operations of the Kepler mission. Doug has and Trent have, I think, well described the mission. Its objective basically is to find Earth-sized planets, particularly in the habitable zone of sun-like stars. Go to the first figure, please. This is a sketch of the spacecraft itself in orbit looking at a planet transiting a star, and that's how we do our photometry. We look for dimmings of a star. The data that I'm going to talk about is of 155,000 stars that we've been monitoring for 4 months. It's of the 1,235 candidates that we have found, and I will describe those as well. But I'd like to start out first with a family portrait of where we've come from. Could I have the next figure? This basically shows you our confirmed planet discoveries. These aren't candidates, these are confirmed planets. In the first season, we were able to find the top row there, 4 planets bigger than Jupiter, and they're compared to Jupiter there, plus a planet that was about the size of Neptune. That's the green object down in the bottom line. The giant planets were a surprise. We didn't think we would find that many. Certainly the one on your far left was an even bigger surprise. It is a planet with one of the lowest densities ever found. This enormous planet, bigger than Jupiter, has a density of styrofoam. Just astounding. The Neptune was a surprise in that it's extremely close to its star. It's very hot, and you'd think that that would expand it and its density would fall. That is not the case. Another surprise. And this last year, one of the things that we were able to confirm was a star with 3 transiting planets, and that's shown in the bottom row. 2 of these planets, 9b and c, are planets about the size of Saturn, and one of them, that little blue object there, is a planet 1.6 times the size of Earth. So we're down in the super-Earth size. A few weeks ago, the start of 2011, we had another announcement. That is Kepler's first rocky planet, a planet 1.4 to the size of the Earth and a density greater than that of the Earth. So it's obviously a rocky planet of some type. So we're moving into the direction we want, from the bigger, easier planets to the smaller planets that might harbor life. So let's go and talk about not what we had found up to today, but look at the data itself that we released last night. Could I have the next figure, please? When we started out, this was our field of view. It covers 100 square degrees of sky. You see 3 yellow points there. These 3 were planets that were known before we launched. They were in our field of view, and of course made measurements of them. But let's look at the same field of view after looking at 4 months of Kepler data. Next figure, please. This are those 1,200 candidates. We cover the field of view with all sorts of candidates. Let's look at the next figure. We measure the size of these objects. We can tell you which are Earth size, which are Neptune size, which is super-Earth size, and you see that in color. The blue dots are Earth-sized planets, Earth-sized candidates, not yet planets. The green ones, the yellow ones, are super-Earths, up to twice the size of the Earth, but still planets that, if they're confirmed, might very well have a solid surface people could walk on. Then we have the Neptune, the size, and the giant planet sizes. So a huge range of planets throughout this field of view. Could I have the next figure? This gives you the numbers of what we have found. 68 Earth-sized candidates. Candidates up to 1.25 the size of Earth. Some of these candidates smaller, considerably smaller than the Earth, closer to Mars size. Then we have the 288 candidates that are somewhat bigger than the Earth. 662 Neptune-sized candidates. As Doug mentioned earlier, in the 15 years of observations, the total number of known planets that have been discovered is like 520. just this group alone of candidates, 165 Jupiter-sized objects, objects that are even bigger than Jupiter, and we're not quite sure what they are. And so there's 19 of those as well. Let's go to the next figure, please. One of the things that we want to do when we find these candidates is find candidates in particular around stars like the Sun, because there's all sorts of stars out there. Giant stars that have engulfed their planets, various stars that are burned out. We would like to find candidates around stars like our own. And this figure shows that if you look at the Earth-sized candidates and the super-size and the Neptune size, all of those are centered. The maximum number is around the temperature of the star, the temperature of our Sun. So these stars are very much like our Sun. There's a variety that you see there, but most of them are around stars like the Sun. And of course, that didn't happen by accident. It happened because before we launched that mission, our co-investigators, led by Dave Latham at the Smithsonian Astrophysical Observatory, used ground-based telescopes to observe 4.4. When we look at these candidates, again, I've broken them into 4 groups. The blue group there, Earth size, and the green groups, super Earth size, and Neptune size, and the Jupiter size. One of the things we see is the number as a function of the orbital period in days. And you see that each of these curves falls to the right. It gets fewer and fewer as you get to larger and larger orbital periods. This occurs because it's harder to see planets further out. The chance of seeing them is diameter of the star over diameter of the orbit. So as you move further and further out, it gets more and more difficult. Fewer and fewer of these candidates and these planets. It gets more difficult as you look for planets toward the habitable zone. The other thing that you notice is there's a peak. The peak here is between 2 and 4 days. And that occurs for every one of the groups. And the thought here is what's happening is that when planets form, they form an accretion disk. And that accretion disk takes momentum and energy from these planets, and they spiral toward their star. And so if they come spiraling in and that orbital period matches the rotation period of the star, tides rise on the star and on the planet such that the star can transfer its rotational momentum to the planet and stop the planet from crashing into the star. And so that's sort of a storage bin of these planets. So we see that very, very clearly in this data. But then you see there's a big dip for periods shorter than 3 or 4 days. And clearly it's easy for us to see short periods planets because they give us so many transits. More transits, the easier to detect them. So this is real. And the implication here is that some of these planets, when they came spiraling in, didn't come in with synchronized with the rotation of the star. And so they continued on their way in and did dissolve into the star. On the other hand, we see some that are still there, and that might mean they were lucky. They simply came in toward the star, and the star lit up, blew away the accretion disk, and now they're safe. Or maybe they're not so safe. They still have tides on those planets, and they may be on their way in to the star yet. So areas of investigation that many scientists will be looking at in the coming months and years. Could I have the next figure, please? When we started out, people had found planets around other stars, and people had found them with the transit technique that we use, what Kepler's contributed last June. Next figure, please. You can see all these purple dots, and you can see that most of them are quite a bit smaller than Jupiter. Most of them are between Earth size and Neptune size. Further, they're not at the shortest periods, they're at much longer periods. So again, a movement toward the lower right-hand corner. Next figure, please. This is what we released yesterday. This is all the data from those 1,235 candidates, those 150,000 stars shown here. And now you see, again, many more planetary candidates closer to the size of the Earth. And in fact, if you look, a lot of them are below the size of it. These objects are getting down toward Mars size, in fact. So we are seeing smaller candidates. And they're moving to the right to longer orbital periods. You can still see there's a little gap there that we want to go to in the lower right-hand corner. But we ought to talk about the temperatures of these candidates. If they're too hot for life, we want to know that. We want to know their temperatures. Are they cool enough so they could have liquid water on the surface? Could they have